What up, Chem peeps? Dreams are coming true. It's another free response practice. Hydrazine is an inorganic compound with the formula N2H4, part A. In the box below, complete the Lewis electron dot diagram for the N2H4 molecule by drawing in all the electron pairs. Alright, well, we know that the hydrogen has to have a single bond. That's it, that's all it can have. And recall that atoms of nitrogen typically form 3 bonds. Well, if each of them is already bonded to 2 hydrogens, that indicates that the bond between these 2 atoms of nitrogen in this molecule is going to be a single bond. But remember, nitrogen strictly follows the octet rule, which means that it's got a lone pair of electrons up here. Also, don't forget the lone pair of electrons. You're asked to draw in all the electron pairs. They're already feeling lonesome by themselves. Don't leave them out. Boom! 1 point. Part B. On the basis of the diagram you completed in Part A, do all 6 atoms in the N2H4 molecule lie in the same plane? Explain. Easy. No, they do not lie in the same plane. The molecular geometry surrounding both nitrogen atoms is trigonal pyramidal. How do I know that? Come back up to the molecule. About this nitrogen, we've got 1, 2, 3, 4 regions. So the electron geometry is going to be tetrahedral, but the geometry of the atoms is going to be trigonal pyramidal. Same thing goes with the nitrogen on the right-hand side. 4 regions of electrons for a tetrahedral electron geometry and a trigonal pyramidal molecular geometry. Therefore, the molecule as a whole cannot have all atoms in the same plane. Boom. Part C. The normal boiling point of N2H4 is 114 degrees Celsius, whereas the normal boiling point of C2H6 is negative 89 degrees Celsius. Explain, in terms of the intermolecular forces present in each liquid, why the boiling point of N2H4 is so much higher than that of C2H6. Now, if you're confused by this, let's draw out a molecule of C2H6. And I'm going to do it right next to my molecule of N2H4. Alright, once again, all of my hydrogens will be singly bonded to those carbons. Carbon typically forms 4 bonds, so once again, we're going to have a single bond connecting these 2 central atoms. So N2H4, C2H6. Relatively low boiling point, relatively high boiling point. Let's explain in terms of intermolecular forces. N2H4 is a polar molecule with London dispersion forces, dipole-dipole interaction, and hydrogen bonding between molecules. C2H6 is a nonpolar molecule and only has London dispersion forces between molecules. It takes more energy to overcome the stronger intermolecular forces in N2H4, which results in a higher boiling point. Boom! Make sure that you explain in terms of intermolecular forces for each liquid. So many times, students like to say, oh, I got N2H4 on lock. I'm just going to explain the intermolecular forces here. But you've got to explain in terms of each of the liquids. Part D. Write a balanced chemical equation for the reaction between N2H4 and H2O that explains why a solution of hydrazine in water has a pH greater than 7. What the heck? Okay, let's just take a breath. We're told that the pH is greater than 7 when we place N2H4 in water. Now let's think about why. What thing in solution is going to cause a pH to be greater than 7? Oh, the hydroxide ion. So what must have happened here between my N2H4 and H2O to form some hydroxide? You guessed it, N2H4 accepted a proton from water, leaving the OH minus ion. So what's left after N2H4 accepts a hydrogen? N2H5 plus. Now, if you really want to knock the socks off your AP graders, is N2H4 going to be a weak base or a strong base? We know it's acting as a base because it's accepting a hydrogen ion because it's forming hydroxide ion, but this is one of our weak bases, so it's probably best to write this as an equilibrium arrow. N2H4 reacts in air according to the equation below. Boom. Part E. Is the reaction an oxidation reduction, acid-base, or decomposition reaction? Justify your answer. Alright, so hopefully we can eliminate decomposition right away. This is not one thing breaking down into smaller parts. We're starting with 2 things here. Hopefully you can recognize that this is not an acid-base neutralization reaction. You might think so initially, because in acid-base neutralization reactions we do form water. But your acid-base neutralization reactions form water and a salt, and its reaction between an acid and a base. And although we identified N2H4 as a base above, O2 is not going to act as an acid here, which means that oxidation reduction is our best bet. However, in order to get the point here, we have to justify our answer. And we can justify that it's an oxidation reduction reaction by confirming that there's a change in oxidation states. So I like to start with the free elements. Oxidation state of oxygen by itself is 0, nitrogen by itself also 0. In the compound N2H4, I'm first going to assign an oxidation state to hydrogen, plus 1, which means that the oxidation state of nitrogen in N2H4 must be minus 2. In water, I'm going to do the same thing. Assign oxidation number to hydrogen first, plus 1, which means the oxygen here will be minus 2. The reaction is an oxidation reduction reaction. Let's be sure to justify. The oxidation state of nitrogen changes from minus 2 to 0, while that of oxygen changes from 0 to minus 2. Nitrogen has been oxidized, oxygen has been reduced. Part F. Predict the sign of the entropy change, delta S, for the reaction. Justify your prediction. Alright, let's head back up here and take a look at the reaction. Thinking about entropy or disorder, notice that we start with 1 mole of liquid, 1 mole of gas, and we form a total of 3 moles of gas. And recall that the gas state is more disordered. It's a greater entropy. The delta S for the reaction is predicted to be positive. Let's justify. There are 3 moles of gas produced from 1 mole of liquid and 1 mole of gas, indicating a net increase in entropy. Things are getting more disordered. Alright, that brings us finally to part G. Indicate whether the statement written in the box below is true or false. Justify your answer. Alright, let's tackle this box. The large negative delta H for the combustion of hydrazine results from the large release of energy that occurs when the strong bonds of the reactants are broken. Oh man, let's go back up and take a look at this reaction. Notice that our delta H is very negative, indicating a large release of energy overall. But let's take a closer look at this statement in the box. The statement indicates that the energy is released when the strong bonds of the reactants are broken. Now this is a common misconception. Is energy released when we break the bonds of the reactants? No. You have to put energy in to break the bonds of the reactants, and then energy is released upon the formation of those product bonds. Remember that with a chemical reaction, you have to put energy in order to break the reactant bonds, and energy is then released upon the formation of those product bonds. The statement is false. Energy is released when bonds are formed, not when bonds are broken. Boom. Done.